Early electrical grids faced a massive physical hurdle. Moving power long distances using standard voltages resulted in catastrophic heat loss, making long-range transmission impossible. This happens because electrical lines have internal resistance, which converts moving current into waste heat. Because heat loss increases with the square of the current, the most efficient way to move power is keeping the current as low as possible. To do that while still delivering the same amount of energy, the voltage must be pushed to extreme levels. The electrical transformer is the mechanism that allows the grid to function under these constraints. It steps voltages up for efficient transport across a state, and then steps them back down for safe use in a home. Establishing a global power network required a physical machine capable of restructuring the electricity's voltage and current to suit its destination. These notes detail the basic architecture to achieve that transformation. A transformer is defined as a device based on mutual induction. Its function is to transform an alternating voltage from one circuit to another at a greater or smaller value. The physical foundation for this process is a closed, square loop known as a soft iron core. On one side, we wrap an input wire called the primary coil, where the initial alternating current enters the machine. Alternating current flowing through the primary wire generates a fluctuating magnetic field. The iron core captures this field, directing the magnetic flux through the loop. On the opposite side, we place a secondary coil. As fluctuating magnetic fields pass through these wires, the magnetic flux induces a new current, which exits to the external circuit. Since the primary and secondary wires are physically separated, the iron core acts as a bridge, transferring energy between them purely through magnetism. The degree to which the voltage changes is determined by a strict geometric relationship, the ratio of the wire coils on the input versus the output. This relationship is a simple ratio. The primary voltage divided by the secondary equals turns in the primary divided by turns in the secondary. To build a step-up transformer, the secondary coil must have more turns than the primary. Because there are more loops of wire on the output side for the magnetic field to interact with, the resulting voltage is scaled up. Conversely, for a step-down transformer, the secondary coil is built with fewer turns than the primary. With fewer turns to intercept the magnetic field, the voltage drops. The transformer acts as a physical multiplier for voltage, governed by the basic algebra of how the wire is wrapped. If we can increase voltage indefinitely by simply adding more coils, it might seem like the machine is generating free energy. Physicists use the model of an ideal transformer, assuming 100% efficiency. The laws of thermodynamics apply. Total power entering must exactly equal power leaving. Since power is voltage times current, primary voltage and current must equal the secondary. This creates an inverse relationship. If the secondary voltage is scaled up, the secondary current must decrease proportionally to keep the total energy balanced. This allows us to complete the ratio shown in the notes. The voltage and turns ratios are inversely tied to the current. In a theoretical system, any gain in voltage is balanced by a loss in current, preserving the conservation of energy. In the real world, no machine achieves this perfect transfer. The physical materials used to build a transformer impose practical limits on its performance. For actual engineering, we calculate the performance of a non-ideal transformer. We measure this using efficiency, or eta, the percentage of input power reaching the output. Expanding the power variables calculates the exact percentage of energy lost during transformation. Because of these physical constraints, eta is always less than 100%. The materials of the transformer itself absorb a portion of the energy as it passes through. The notes list 4 specific physical phenomena responsible for these energy losses. The first is flux leakage. No core is perfect, and a small amount of magnetic field escapes the iron before reaching the secondary coil. Second is the resistance of the windings. Copper wire is an excellent conductor, but it still has some resistance, which converts current into waste heat. Third is hysteresis. The alternating current constantly reverses the magnetic alignment of the iron core. This repeated switching creates internal friction that dissipates energy. Finally, the magnetic field induces eddy currents, small circular electrical paths inside the solid iron core itself, which steal power from the circuit. While the mathematical theory behind this is straightforward, the actual design of a transformer is a constant effort to mitigate these 4 thermodynamic drains. Despite all of these unavoidable heat losses, the transformer remains the standard mechanism for managing power distribution across the globe. It allows us to span thousands of miles with high-voltage transmission lines and then safely step that power down to the millivolts required by modern electronics. The massive industrial substations that surround our cities are direct applications of these foundational physics. Our entire electrical infrastructure is built on the simple geometry of wrapping wire around a block of iron.